It's a pleasure to participate for this event. I'm Allan Albuquerque, visiting research in Federal University of Pernambuco. We have some co-authors from this work. It's the Professor Flora In from the University of Waterloo, and also Professors Leandro Danielski and Luis Strajevich from UFPA. The work is the keynote reactive separation process applied to biodiesel production, phase equilibrium, design, optimization, and technical-economic assessment. Well, I'll talk a little bit about our location. We are located in Brazil, South America country, more specifically in Pernambuco state, that is located in the northwest. The capital is Recife, where we are in the Federal University of Pernambuco. We have at least, before the pandemic, 40,000 people per day, including students and professionals. We are located in the Department of Nuclear Energy, and we have some financial support from the training program of human resource that are financed by the Brazilian National Agency for Petroleum, Natural Gas, and Biofuels. Then I've been working in the PRH, where we are focusing on some research in characterization and simulation of reservoirs, environmental biotechnology, and renewable energy. In that case, my field is renewable energy, and we have the bioenergy group where I'm located. And also we have an experimental biorefinery for solid organic waste. Then our group, we have some objectives. For instance, to develop the organic waste management in our campus, and also to train some students and professionals, to develop research, and also to transfer low-cost technology for control side. We have focusing some work in sustainable energy production from biomass and waste, for example, anaerobic digestion using food waste and residuals biomass and palm, for instance, and also second generation bioethanol production based on food waste and also other raw materials, and also biodiesel production using wasting cooking oil in other kinds of process. We have anaerobic digestion reactor using food waste to produce biogas to be using electricity and also for cooking gas, and also a pilot plant for biodiesel production using waste cooking oil that is used to for buses from our university. We have also biofertilizer produced to be used in the university. Well, starting my presentation, I'll talk a little bit about the biodiesel, focusing in that case in Brazil, since we know that the three largest production around the world is US, Brazil, and Indonesia. And in Brazil, we started to be worried about biodiesel in 1970s. Biodiesel is a fuel composed of alkyl esters and can be used in the internal combustion engines and can replace partially or totally the petroleum diesel. After this event in 1970s, some economic reasons Brazil didn't stay too much interested in biodiesel, but in 2004, because of the Brazilian National Program for Production and Use of Biodiesel, we started to pay more attention. In 2008, with the ANP, they imposed 2% of addition of biodiesel to this petroleum diesel. And since then, we had some macroeconomic, social, and environmental reasons, and now we have in this year 10% of biodiesel on petroleum diesel. It's expected to have in 2023 15%. The main raw materials used in many countries are edible oils and also in Brazil. But for instance, soybean oil is very important in Brazil. But the problem is that these raw materials can represent 85% of the biodiesel cost. For this reason, many authors and researchers are trying to develop biodiesel production using non-edible oils, such as rapeseed oil, crude tall oil, and the others. Another option is residual oil fats, ROF, that can be composed of waste in cooking oil and animal fat and waste. The problem is these raw materials, they have high content of free fat acids, the FFA, and they can be sold as yellow grease with content less than 50% or brown grease with greater than 15%. The advantage to use these raw materials, one of these decreasing negative environmental impacts caused by the improper disposal of this waste in cooking oil, for instance. And another is because they decrease raw material costs. They can represent 40 to 70% less than using edible oils. We know that the conventional process to produce biodiesel is based on the transacidification reaction using alkali catalyzed in that case. And we have then vegetable oil composed of 3-acylglycerol that reacts with 3 molecules of alcohol to produce 3 alkyl esters and also glycerol. The problem is ROFs, they have high content of FFA, free fatty acids. In that case, we need a pre-treatment to increase the yield. Then the conventional process for these raw materials, we have a pre-treatment before the transacidification reaction, where we use esterification reaction to the free fatty acids in presence of alcohol and ask the catalyst to produce ester, alkyl ester, and water. The problem is that we have more equipment in the pre-treatment, increasing the capital cost, and also we have a glycerol washing step to remove catalyzed water and also the methanol excess in that case, increasing also operation costs. For these reasons, some autos are trying to develop alternative process, more cheaper process. For instance, supercritical conditions to develop both reactions, esterification and transacidification in the same reactor, or to try to separate FFA from the 3-acylglycerols, or to use solid catalyzed that, in my opinion, must be the most promised one. Many authors are trying to develop solid catalyzed that can increase conversion, be tolerant to water and FFA, with good reusability, operate in moderate conditions, and with low molar rate of alcohol to oil. In that case, we'll use in this work the soft aspen plus aspen tech to design, simulate, and also optimize some process to make comparisons. There are other options, but we are focusing in this work in solid catalyzed in reactive distillation. Reactive distillation, in that case, we can use separation and reaction in the same equipment instead of to use a reactor in distillation column. In that case, we can decrease capital costs, and also we have a chance to decrease solvent costs because we have a reflux ratio of alcohol here, and also alcohol vaporizing in the column. We also try to use low-cost raw materials, such as residual oil fats and crude tall oil, and in recent works, we are working with ethanol. In that case, we will present some results from alternative process based on the design and analysis of feasibility, combining reactive distillation and solid catalyzed inside packing. In that case, we have a catalytic distillation column using these 2 kinds of raw materials. We also noted absence of a phase equilibrium model applied for the reactive distillation column. Then we developed this phase equilibrium, and also some optimization in the process in heat integration flexibility studies. The objectives then investigate innovative reactive separation process to do reaction and separation in the same equipment using these low-cost raw materials. Also to optimize separation of free fatty acids from the oil, design this process and make a comparison about techno-economic aspects for a reactor distillation or a reactive distillation column. estimate some thermophysical properties, and also construct a data bank and phase equilibrium modeling to validate this modeling, and also design the process, optimize, and make comparison related to techno-economic aspects, doing some optimization and heat integration flexibility study. The first paper that we published after the development of this work in my PhD, optimization of the extraction of free fatty acids applied to biodiesel production to achieve these objectives. Then this is the conventional process that I told about before. And the idea here is to use an extraction column with methanol to be a separating agent of triacylglycerol and free fatty acids, and carry out the reactions in separate reactors to produce biodiesel. In that case, we try to optimize this column based on 3 variables: number of stage, temperature, and solvent to feed ratio, and also investigating 2 cases of yellow and brown grids. We also designed the process to produce biodiesel and compare these 2 options. The technical standard for biodiesel is given by ANP, and also we try to obtain pharmaceutical glycerol, and for economic feasibility, for comparison, we use these economic indicators as total analyzed cost, break-even price, payback period, and return of investment. We estimate some thermophysical properties for acylglycerols because in the software it was a problem to represent. Also developed thermodynamic modeling for the liquid-liquid equilibrium for the separation. And we did also a full factor design with the 3 input variables, including the 2 response here, the cost and the free fatty acids mass fraction in the oil stream to reduce these values. We optimize this process for the yellow grease case and brown grease case, and we identify these optimized conditions, helping to minimize costs in this process, being also technical feasible to produce biodiesel. This is the process A, and B, the pretreatment unit, that is the same for both processes, where we have the FF separation here. After that, we have the transesterification unit for process A, using a reactor and a distillation column. In process B is different because there is a unique column to do reaction and separation, the reactive distillation column. In both processes, we achieve the biodiesel standard and also glycerol pharmaceutical. We have here investment cost was lower for process B because of just a unique equipment. We have some indicators very close between this process, and maybe environmental aspects could be the indicators to be chosen the best process. The second paper, we identified absence of phase equilibrium in the reactive distillation column, capable to represent the vapor-liquid equilibrium. In that case, also to represent the vapor-liquid and the liquid-liquid equilibriums. In that case, using a solid acid catalyst capable to do esterification and transesterification at the same time, the reactive zone, and we also validate the experiments reported in the literature. Then, to achieve these objectives, to estimate thermophysical properties, construct the data bank, develop the phase equilibrium modeling, and to validate its modeling. These are the steps carried out. 2 words were chosen to support the experimental data. One from solid acid catalyzed process using a catalytic distillation to produce biodiesel by esterification simultaneous to transesterification, and also homogeneous alkali catalyzed process, well known. Then the thermophysical properties were estimated using group contribution, in this case vapor pressure, and constituent fragments using constituent fragments approach for other properties. We developed the data bank, in that case, VLE data bank with almost 6,000 data. We classify them and also evaluate the thermodynamic consistency only the system that has passed in this test we use. The LELE data bank, it was almost 2,500 data. In the VLELE data bank, we had just 46 data from alcohol, alkyl esters, and glycerol system. We developed 3 parameter sets for the NERTL model. One applied for esterification and transesterification reactions inside Aspen Plus, and another NERTL3 that we can use in any software without the Aspen license. And NERTL2 is applicable for transesterification reaction. And the VLE diagrams are well represented for the parameter set, and also LELE diagrams. In that case, one parameter set can represent the 3-phase equilibrium. And also the VLE diagrams. Of course, observing the deviations, NERTL3 presented lower deviations for VLE and LELE, but for VLELE, NERTL1 should be chosen to using modelings. We validate this modeling also using some kinetic modeling for the solid acid catalyzed process, then obtaining yields and temperature profile very close to the experimental. And also for the homogeneous alkali catalyzed process, with better results using NERTL2 that is specific for transesterification reaction. The third paper is reactive separation process applied to biodiesel production from residual oil and fats, design optimization, technical economic assessment using solid catalyst. Then we studied first the base case process based on a catalytic distillation column, where we have both reactions here, esterification and transesterification, using this solid catalyst, and residual oil fats and methanol are in liquid phase. And we produce biodiesel and glycerol here, and methanol XX is recycled. And we compare with alternative process using catalytic absorption column. In that case, because we have a low reflux ratio here, in that case, we could remove this condenser, then we remove the condenser and also the reboiler to compare if the biodiesel product is cheaper or not. With both reactions, again, the same catalyst, and the methanol in that case is fed in vapor phase. The third process is an industrial process found in Brazil based on the route of hydroesterification, where you have a plug flow reactor to produce by hydrolysis. And after that, we have a esterification reaction using a catalytic distillation to produce biodiesel and make comparison with the other 2 processes. Then trying to achieve these objectives, the design, optimization, technical economic assessment using ROF, and doing some optimization, heat integration, flexibility study. The same biodiesel technical standard was used, and also economic indicators. The optimization was done by local, by decision maker, and also by global optimization using objective function, total analyzed cost, adopting utility cost, installed cost, and waste treatment cost. In that case, we connected the Aspen Plus with MATLAB using the optimization toolbox. This is the base case process, catalytic distillation with esterification and transesterification in the same time. Then we don't have the pretreatment units, and we produced glycerol and biodiesel. We made some optimization in the methanol feed flow rate and also other variables. And we studied also the catalytic absorption column, and we removed in that case the reboiler and the condenser. And for these both 2 processes, we identified we achieved the biodiesel standard and also glycerol. The third process, hydroesterification, using a PFR reactor for hydrolysis, and a catalytic distillation column to produce biodiesel. And again, we obtained biodiesel achieving the standard. But process C1, that is hydroesterification, we have in that case a higher capital cost, in much higher energy usage, and also operation costs, waste treatment costs, and CO2 emissions. In that case, process based on catalytic distillation column and catalytic absorption column were the better process to be used in solid acid catalyzed with residual oil fats. But because process based on catalytic distillation column is much more simpler than the catalytic absorption column, we decided to do a global optimization for this process, and then changing 10 variables, we identified them $2.5 million per year of reduction in the optimization. We also did a study of flexibility because we started with a FFA composition of 15%, and the industry can receive 5% or 25%. Then we designed an industry that is capable to work with this composition. We obtain a biodiesel with a price is 74 cents per kilogram. That's very close to literature. And the last paper, we have a new process for biodiesel production from tall oil using catalytic distillation. Then tall oil, it's a byproduct obtained from crafty pulping process in paper industry. In that case, is very well developed in the US and other countries as Canada. And crude tall oil in that case has free fatty acids, resin acids, and neutral compounds. And we need to separate water, for example, using a dehydration step after we have a distillation column to remove tall oil pitch. And after that, the conventional process, we have more 3 columns to remove tall oil rosin containing resin acids, and distillate tall oil with a mixture of free fatty acids and resin acids, and tall oil fatty acid that is the important product to be used to produce biodiesel. In that case, we needed to achieve 99.28% to be technically feasible to produce biodiesel. The alternative process that we propose is based on 3 distillation columns instead of 4 distillation columns. Then in that case, we have only 2 distillations here, and the last one, we have 3 products produced, distillate tall oil resin, and tall oil fatty acids. In that case, we found 99.28%, and it was possible to produce biodiesel using a catalytic distillation column with a solid acid catalyzed, that in that case, it's a commercial one. The objectives are the same, but in that case, using crude tall oil. The standard for technical assessments is the same, and also the economic indicators. We studied 3 crude tall oils different. We started with a sample from US using 6 different kinds of fat acids, 6 resin acids, a neutral compound, and water. In that case, for the pre-treatment step, we used the UNIFAC model. And after, when we obtained the tall oil fatty acids, we had much higher concentration of oleic acid. For this reason, we used for esterification reaction the NERTL model with this pseudo complement. The feed flow rate, it was based on industry in the United States. We needed also to represent the thermophysical properties of resin acids using this model for resin acids. And kinetic model was a user one based on Fortune code constructed based on the kinetics from Tesla. We also investigate a catalytic divide wall column because we were worried about the water that could be responsible for deactivate the catalyst. Then we tried to remove water here, and a flexibility study using 3 types of CTU. This is the validation of the kinetic modeling. Process A using 4 distillation columns, we obtain all byproducts and also tall oil fatty acid, but in that case, it was not possible to obtain 99.28%. Then this process was not feasible to produce biodiesel. In contrast, process B using 3 columns, it was possible to obtain this concentration. Then we tried to use to produce biodiesel using a catalytic distillation column for esterification reaction, and we achieved the biodiesel standard in that case. We compared this process and process B because there is 3 columns. We had in that case lower capital cost, and also we identified other energy usage and indicators for economics much lower than the process A. We also obtain a conclusion that when you have higher concentration of free fatty acids, you have a higher profit. In that case, because if you have a higher concentration of resin acids, you need more energy to separate them, and in that case, you have a higher cost. This is the results from the biodiesel production, process C. And we also investigated the catalytic divide wall column, but it was not technically feasible because we identified temperatures greater than 300 degrees that can deactivate the catalyst in the reactive zone. These are some profiles from the column. And we also carry out global optimization for the process C to produce biodiesel. And we also made a study of flexibility using 3 different kinds of CTOs. And we obtained at least 82 cents per kilogram for biodiesel for Scandinavia, or for the sample from Canada, at least $1 per kilogram. Recent works that we are developing, we are trying now to develop this process applied to biodiesel production using ethanol. Then we have some co-op students working this phase equilibrium modeling based on the NERTL and UNIQUAC models. And we also have some students working the validation of these profiles inside the column, and also to design, optimize, in techno-economic assess this process using a solid acid catalyst. We also published another paper in this area using another reactive separation process. It's an integrated process of absorption and reactive distillation. In that case, we have a reactive zone in the top and absorption zone in the bottom. Then we use the azeotropic mixture of ethanol water in the vertical phase, being fed in the column in the bottom. And glycerol is used to dehydrate this water, and we obtain here ethanol close to anhydrous to use for the reactive section using a transesterification reaction. Then we obtain very interesting results to produce biodiesel, achieving the standard. Well, I do like to acknowledge all the organizations and labs and financial support from these organizations. This is my contact. Our group are open for any collaborations, and I prepare for questions if you have. Thank you very much.